All right, can I have everyone's attention? I want to introduce our speaker today, and also I want to make a couple quick announcements for the students that are taking, especially the students taking the 4372 course. You guys, in about 2 weeks, you're going to have your presentations in here, your final presentation for the class. And so I'm going to need everyone to email me the title of your presentation as soon as possible, so that I have all those. And so, and once you email me your title, I'll email you back with information on any of the reports I'm missing from you guys. So that way you know everything is squared away. And if you do have a report that I'm showing is missing, then you know to get it to me before the end. So I want to introduce our speaker today. This is Stephen Koontz, who is at NASA Johnson Space Center. He's been there for a few years as the ISS System Manager for Space Environments. He has got he's got a background in chemistry, in analytical chemistry, but we're not holding that against him today. Where he went to got degrees from University of California, Berkeley, and University of Arizona. Also, he has won several awards from NASA, including the NASA Exceptional Service Medal, the Astronaut Personal Achievement Award, the Rotary Stellar Award, the NASA Johnson Space Center's Director's Commendation Award, and the NASA Silver Achievement Medal. And so today he's going to be talking about spacecraft charging, and this is an interesting problem because, as you'll hear, it involves a lot of the things that we learn about in electrodynamics, but it's in a different environment because the space station is definitely not grounded. So with that, I'll turn it over to you.
Well, it is in a sense, and this will not seem like an academic physics lecture. This talk was originally prepared and presented to the NASA Engineering Safety Council at one of a series I did. It's kind of interdisciplinary. There's a lot of jargon, but bear with me. The fact that the word hazard appears 3 times on the cover page should indicate to you that this has something to do with safety, reliability, and mission success. First, a summary of what we're going to go over. What is the hazard cause we're talking about? It's the accumulation of electrical charge on spacecraft and spacecraft components produced by the spacecraft interacting with space plasmas, energetic particle streams, solar UV photons, free electrons and photons typically drive these processes, and in addition, the spacecraft can do it to itself with electric propulsion, ion and electron guns, and other gadgets that are fun to play with. What are the hazard effects? Dielectric breakdown arcs that cause problems for your avionics and your power system. And interesting things can happen. Can't happen in low Earth orbit, as I'll show you later, but when we start moving outward beyond LEO to Cislunar space for the Gateway program, an Orion vehicle approaching the Gateway platform and making contact with it when one of them is at 400 volts and one of them is at 0 volts can be interesting, and it's something to avoid. For years, NASA has put first contact bleed resistors on spacecraft, even if you don't need them in low Earth orbit, but whether or not that works depends on how rapidly the spacecraft is charging compared with how rapidly the bleed resistor equalizes the charge. In many cases, the bleed resistor just gets hot, nothing happens, and you get your big jolt anyway when the metal surfaces make contact. The best way to control this hazard is through safe and verified design. A lot of spacecraft were destroyed in the 70s and 80s while everyone was figuring out how this works. And if you take advantage of lessons learned to date and are familiar with NASA and DoD standards and guidelines on this subject, your spacecraft will survive most of the time. And if you blow it off because you've got schedule and budget problems, you may find other things blowing off too later in the program. Basically, material selection, grounding and bonding practices, electromagnetic interference, and electromagnetic compatibility and screening for potentially hazardous configurations, verified during acceptance testing, is how you put a spacecraft in geosynchronous orbit that will work for 15 years without a problem. Unfortunately, not everyone knows what the requirements mean, and we've had a number of cases where that was done and it slipped through the cracks. And at the end of this talk, you'll see a particularly egregious example in which $1 billion spacecraft was destroyed by failure to do that. People say the space environment destroys spacecraft, and I maintain it really doesn't. The design and operations team destroyed the spacecraft by ignoring the environment up front. It's 100% human error, but that's just me. It looks that way to me. You can use in-flight operational hazard controls, and at the end of the day, you want to test like you fly and fly like you test to the extent possible. Aerospace Corporation keeps going on about this, but in many cases, you really have to compromise on that ideal. Presentation outline, we'll summarize spacecraft charging processes, look at some simple charging discharge circuit, talk about materials, configuration, and operations effects. Compare internal and external charging, look at the charge balance equation that lets you quantify all of this. Then we'll talk about some space plasmas and energetic particle environments, work a couple of simple examples. One, how space station charges in an otherwise benign charging controlled environment, the ionosphere, because its PV array and its physical size lead to voltages occurring anyway that collect current from the ionosphere. Next, we look at auroral charging in LEO and low polar orbit, which is kind of a precursor to seeing how things are going to be out in geo and cislunar space and interplanetary space during certain space weather events. Space weather drives a lot of this. In the ionosphere and the magnetosphere, radiation belts, geosynchronous orbit, and beyond, all the way to Mars, space weather generated by solar activity is going to change your charging environment, and there will be days when you're going to need a lot of protection against that, even though it's benign most of the rest of the time. Last, we'll look at a particularly interesting example of what happens if you ignore all of this in design, development, and test, and that spacecraft didn't even last a year on orbit. So, why do we care about this? Safety, reliability, and mission success is why we care about this. The table on the upper right gives a number of anomaly records compiled by Aerospace Corporation up to 2001. You can see internal charging and surface charging contribute almost as much as single event effects and a lot more than meteoroid and debris impacts for that class of military and commercial satellites we're usually dealing with. A more recent study sorts out 84% of the failures to human error. And as I indicated before, I think the rest are really human error too. It isn't often that the environment exceeds your design environment and you get hit anyway, but that can happen. The most common hazard effects of the spacecraft charging hazard cause are avionics system failures and anomalies, electrical power system failures and anomalies, surface property degradation caused by arcing, which as it's turning out is a big deal for the GPS constellation. They're in a very high-risk charging environment, and surface arcing is causing their PV arrays to lose power much more rapidly than anticipated as a result of contamination from the arcing events. And even increased attitude control propellant usage, just because these surface arcs can be propulsive. That's led to early end of mission for some communications and military satellites. And without putting too fine a point on it, if you're 6 months out from Earth and you lose your electrical power system, everybody dies. So we can't let that happen. Spacecraft charging. Any process that produces an electrical potential voltage difference between the spacecraft and the surrounding space and plasma environment, absolute or frame charging, as well as voltage differences between electrically isolated parts of the spacecraft. We call that differential charging. The electrical potential differences result from the separation of positive and negative charges in the spacecraft, spaceflight environment, or both, with an accumulation of an excess of one charge on some specific location. Current balance equations can let you quantitate that, And let's summarize the determining factors now. Flux and kinetic energy of high energy charged particles, anything above 30 kilovolts, 10 kilovolts. Local space plasma density and temperature, as in Earth's ionosphere, the solar wind, or the coronal mass ejection that's causing a big geomagnetic storm as it moves past the planet, and even spacecraft motion relative to local space plasma and magnetic field, which is important for station. Remember, the thing has a 100-meter truss. It's all one piece of metal, and it's flying through the geomagnetic field at 7.8 kilometers per second. You might expect some Faraday induction for that, and yeah, we see a lot of it. During charging and discharging, currents flow through various parts of the spacecraft and can break things. Simple resistor capacitor charging circuits can give you a feel for how this works, and you need to remember that conductors and dielectrics charge and discharge in very different ways. Spacecraft charging isn't magical, though many of my colleagues at JSC have often told me they thought it looked that way, and that's because I've drawn a resistor capacitor circuit here, but these resistors and voltage sources are very peculiar compared to what you see in the electronics lab. The voltage can be coming from heliospheric coronal mass ejections interacting with magnetic fields over hundreds of millions of kilometers. It's not a power supply on the bench with a knob you turn. The resistance or collecting current by the vehicle depends on the plasma sheath around the vehicle, the density of the plasma the vehicle is in. And when you really work the charge balance equation, it's not going to have a visible R in it. You're going to be working with conductances and particle collection rates directly. This other resistance is the resistance of the plasma breakdown arc that appears when that switch closes. And that's kind of exotic too. It also depends, R2 being a discharge pathway can be a function of your active charging control equipment, like a plasma contactor unit. That doesn't look like a resistor either. C is the easiest piece of all this because it depends on vehicle configuration, and fairly simple capacitance equations for free space and dielectric coated structures work really well here and explain a lot. Now, I have been accused of trying to scare people with this, and I'm not really trying to scare people with this. What you're about to see is what happens when you take a piece of acrylic plastic, put it in the vacuum chamber, and hit it for a few minutes with a 1 million electron volt electron beam. Then you vent the chamber. It looks like nothing interesting has happened. You can pick this up and carry it around. But you'll notice the fellow who's about to do this is holding an insulated hammer, and that this is a rubber strip that doesn't conduct the electricity. Because when he disturbs it, something interesting happens. All that energy got released fairly abruptly, and it damaged the plastic. And it's still arcing after the first hit. Now, without putting too fine a point on it, we do encounter megavolt electrons in sufficient density to do this kind of thing, or even 100 keV electrons in the auroral zone. And if this is an acrylic window on your spacecraft that isn't protected by, say, a centimeter of quartz or so, your window can do this occasionally. That's not going to work too well afterwards. And if I'm depending on that window to keep the air inside, it's time to put the spacesuit on. So, spacecraft mission environment, materials, configuration, and CONOPS determine what kind of concept of operations, determine what's going to happen to your spacecraft with respect to charging. Your spacecraft is also able to charge itself in a variety of different ways, especially if it has ion engines. The amount of metallic area on your spacecraft is important because that can collect ions for you and help offset electron collection. But more important than anything else are the properties of the dielectric materials. Secondary electrons are knocked out of the solid when a high energy electron enters it. Secondary electron emission is different for different materials, so in the same environment you can have one plastic at 200 volts and the other at a kilovolt. Photoelectron emission can clean surface charge off spacecraft completely. So COMSATs that have charged to 30 kilovolts in eclipse come out of eclipse, and now part of the spacecraft is at plus 10 volts, the adjacent part is at -30, and interesting things can happen if you didn't design that out with static dissipative materials at the beginning of the day. Static dissipative dielectrics are an important idea here. Spacecraft capacitance and the capacitance of electrically isolated spacecraft components, you can estimate that with simple back-of-the-envelope calculations like this. But the reason I put these equations down is, and compare the free space capacitance for the disk and sphere with the coated thin dielectric coating on the sphere. And when I put the thin dielectric coating on the metal, I've made a capacitor. And the capacitance in that case is A over D. So if you have a very thin dielectric coating on a large metallic object, your capacitance goes up forward as a magnitude or more. Now, that means it'll store more energy, but it also means that it takes a lot more time at a given current to get to a high voltage. We'll see later that space station charges to maybe 18 to 20 volts in an environment that charges a DoD Defense Meteorological Program satellite to 2 kilovolts. It's the capacitance difference and the limited exposure time that does that. Electron kinetic energy is of primary importance here. There have been a couple of papers about proton charging, but it's not exactly convincing that that's important just yet. Maybe there's a problem there. A lot of protons at high energy in those particle events, but we mostly view that as a radiation single event environment problem. Surface charging 0 to 50 kilovolts. Internal to surface charging transition 50 to 100 kiloelectron volts. Internal charging anything greater than 100 keV. But bear in mind that general rule and rough thumb about space radiation environments. There's always a power law. You have a lot more at low kinetic energy than you do at high kinetic energy. That means you've got a big surface charging threat, you've got a big internal charging threat long before you have any kind of single event threat from the protons. Electrons don't do single event effects. And the practical range of concern for geo and cislunar orbits is 0.1 to 3 MeV, and you need about 0.1 to 0.3 centimeters of shielding of some kind to keep that stuff off your printed circuit boards. And here is the range plot that tells you, for example, how much aluminum it takes to stop a 1 MeV electron, and it turns out to be about a centimeter. 3 MeV electron, we'll put it up here. The protons aren't doing much until we're way out beyond 200 MeV, 300 MeV, and then they take over as the electrons fall off. And this little cartoon is supposed to give you a feel for what's going on with the various processes for surface charging and internal charging. In internal charging, the electrons come right through your spacecraft, and bear in mind that COMSATs, military reconnaissance vehicles, that kind of thing in general, don't have a lot of shielding mass because you've got to keep them light enough to launch. So that means if some electrons get through and into your printed circuit board, or on that ungrounded piece of metal you forgot to ground, you're going to have electrostatic discharges of some magnitude on this PC board, on the metal traces from the ungrounded piece of metal that will destroy your avionics. They won't work anymore. Outside on the skin of the spacecraft, we're picking up electrons from the plasma. In sunlight, photons are removing electrons that were picked up from the plasma. You're also picking up some ions. Over here, the same kind of thing is happening with the metal, but if you end up with a big voltage difference between your dielectric and your piece of metal, you can't have an arc, and many of those have been recorded and have done damage. This is a specific example of what it looks like for space station if, as was suspected before flight, we could pick up enough PV array-driven charging to charge up those big pressurized tab modules, which are huge capacitors, and then have a dielectric breakdown arc through that real thin anodized aluminum coating on the aluminum plates. Active electrons are collected by the PV arrays, charge the structure negative. Now remember, the ionosphere is a plasma. It conducts electricity. It's a gas. And one thing all conductors want to do is rearrange charges to null out any externally applied electrostatic or magnetic field. So we have a bunch of ions come in from the ionosphere to try to null that out, and that produces a huge voltage gradient across that very thin anodic film. If the voltage is high enough, it turned out to be between 60 and 160 volts per station, depending on how long you let it cook before you see the arc. Time-dependent dielectric breakdown is an important piece of all this. Then you get a big arc, a lot of damage locally, a lot of electromagnetic noise, and that's actually acting like a little tiny plasma contactor, isn't it? It's removing all that negative charge from the vehicle and getting it back out where you want it to be. And that's what that looks like when you do it in the test chamber. This scale, that's about 14 centimeters. These are all arcs produced when a huge high-speed storage capacitor was attached to that metal plate in the plasma chamber. The huge high-speed storage capacitor representing the station pressurized element with the high capacitance. And this thing was arcing pretty regularly every few minutes for a while in the test chamber, and that doesn't look too bad, and it isn't, and nobody was really worried about that because our EMI, EMC design, grounding, and bonding and all of that effectively nullified the effect inside space station. But fortunately, this hasn't happened at all. We haven't seen this happen on orbit yet. We'll explain why later. However, we have seen other things happen on orbit. And if your PV array is powered and you get one of these little dielectric breakdown arcs so that it can conduct a hot wire with a ground wire or a cells at two different voltages, the power from the power supply feeds the arc, it gets bigger, and this kind of thing happens. Then you can lose your PV array, and various people have in the past. The current balance equation I was referring to earlier, the voltage is the voltage of the spacecraft. We're not referring to explicitly in this simple tutorial toy model about the kinetic energy of the incoming particles. But the bottom line here is that at equilibrium, the total current to the surface is zero. You're going to collect electrons more easily than ions. The surface will go negative until the ion and electron collection are equal. Then we're done. But remember, at Earth orbit at 1 AU from the sun, you can get about 10 to the minus 9 amps per centimeter squared of photoelectron emission, removing electrons from the surface. So if your charging current, the electron current, is a lot less than 10 to the minus 9 amps, you're not going to see any charging in sunlight. It's going to go positive, which is fine. But the part of the spacecraft that's not in sunlight may be at 30 kilovolts already, and that's why we like static dissipative materials. Now, we'll have a quick look at Earth's ionosphere. This only became available recently. I wish we had it in 2000. But you can see there's a map of the world here and a bunch of little dots all over it, and then some colored spaces. The little dots are Digison stations. They're vertical radio transmitters that sound the ionosphere and determine the altitude of the maximum density region at looking up, the first maximum density region you see, and effectively the electron density, because the critical frequency is proportional to the electron density. So we can look and see how that's doing today by doing that, I hope. Maybe, maybe not. There it goes. Okay. So this is the maximum electron density number, the critical frequency, and that's the altitude at which we see the critical frequency. We've got planetary coverage except over the oceans. And we plan to use this if we lose our FPMU for our detection and warning processes for EVA safety on station. But you see this peculiar structure, that's called the Appleton anomaly. And we pick up a lot of charging if we go through that with the PV arrays on station in the wrong orientation. Whoops, I think I shut off the talk. Oh, there it is. Thank you. We've also used this facility in the past without actually having to pay for it. That's the Millstone Hill Radio Astronomy Observatory and Ionospheric Observatory. They use a much higher frequency. It goes completely through the ionosphere, and you need a really big dish to receive the very weak scattered return signal. But that gives you a density and temperature profile for the entire ionosphere above you, albeit at one location, Millstone Hill, Massachusetts. And as I'll show you later, we verified some of our instruments on station when we fly over this and compare their measurements with ours. Moving away from LEO, everything gets interesting, and this cartoon is designed to give you a feel for that, and the fact that there are just a large number of spacecraft working in these environments that have not been destroyed by spacecraft charging. I think we all learned something since 1979 or before, when we were losing spacecraft to these phenomena a lot. And this cartoon obviously isn't to scale. But the reason I like to show it to people is to reinforce the idea that when the moon is full as viewed from Earth, you're in a geosynchronous charging environment. This is not benign anymore like the solar wind. And when there's a geomagnetic storm, you get one out here too. And we have spacecraft observations to that effect. Now that we're planning to put hopefully put a man-tended platform around the moon with international partners and fly Orions there, we have to remember that during Apollo we never went to the moon when it was full as viewed from Earth, although that was primarily for thermal reasons. You don't want to be on the surface of the moon when it's fully illuminated by the sun. It is really hot. And that's why it was always first quarter or last quarter for Apollo. And this gives you an idea of how all of that works. You may have heard something about reconnection. That's a coronal mass ejection sweeping past the planet. We're about to get a geomagnetic storm and aurora from a reconnection event. You may have heard something after the August solar eclipse last year about reconnection events being the reason the solar corona was much hotter than anyone thought it should be, because a lot of energy is stored in those magnetic field structures that gets released by the reconnection event. And I want to emphasize that you just saw a bunch of electrons get fired at Earth. Same time, a bunch of electrons got fired downwind. And if the moon happens to be there, it gets the electrons too. Now, I've been talking about plasmas and energetic particle streams. There's not much to say about energetic particle streams, except in space they're usually isotropic. They don't look like an accelerator beam for the most part. But plasmas are something that a lot of people aren't that familiar with. And a plasma is an ionized gas that conducts electricity and has sufficient density that its plasma parameter, which is the number of charged particles in a typical Debye length or shielding length, is much greater than 1. And the shielding length is much less than the characteristic length of whatever system you're dealing with. And Maxwell-Boltzmann theory applies to all of this. The plasma has a temperature. The electrons and the ions are at the same temperature, but the masses are very different, so the electrons are traveling a lot faster than the ions. That's why you pick up more of them, and your surfaces tend to charge negative. Some other important properties are the plasma frequency. That's how the ionosons, the digisons, work. And the fact that this sheath around the spacecraft contributes to the capacitance is a really big deal and contributes to some of the peculiar phenomena we see on station, where we do charge to extremely high dangerous voltages, albeit very briefly. Briefly enough to say, that's not a hazard, we don't need to control it, but we do need to put that command that causes that on the hazardous command list. So what do these plasmas look like? The gas discharge, which is high density and hot, well, it's not a space environment concern unless you understand that it looks this way inside your ion engine or your Hall effect engine. And a small object in this plasma charges to about -10 volts negative. The ionosphere, a small object is going to be a volt or two at most. Up in the magnetosphere, in the radiation belts in the geosynchronous orbit, we have real high temperatures and moderate densities to low densities, so that at night or in shadow, your structures can go to 10 kilovolts negative, while anything illuminated will be 10 kilovolts positive, unless you have static dissipative surfaces that will even that out rapidly enough to prevent a problem. The solar wind itself is completely benign, plus 10 in sunlight, minus 20 in eclipse. We only have problems outside the magnetosphere, or issues, or whatever you want to call them, if we're in the geotail, or there's a coronal mass ejection going by, or there's a solar particle event in progress. Then it gets interesting and very magnetosphere-like. One charged particle environment of particular interest, since we fly through them all the time, is the auroral charging environment. This is to give you a feel for what that charged particle environment looks like. Electron kinetic energy is 0.01 to 100 keV, and the flux is from 10 to the 2 to 10 to the 6 electrons per square minute, centimeter per second per steradian per electron volt. Now I'm going to emphasize that per EV out here. That means this is a differential distribution, kinetic energy, in contrast to these, where the EV doesn't appear, and that means that, say, at 1 MeV here, we have this many particles of energy equal to or greater than that number. Hence integral, we're adding it up. So that's your worst case charging environment suggested for design by our ultra-conservative friends at JPL, and that's the NASA AE8 minimum, solar minimum model, and that model is going to probably be replaced by AE9 as soon as we think it's ready. AE9 is ready for prime time, which we don't think it is yet. Over here you can see a comparison of the geo environment, the map environment, which is a lunar phasing departure trajectory, and the high Earth orbit environment, which is basically elliptical out to just under geosync. Look at your flux, 10 to the 5, 10 to the 6, 10 to the 7, and you've got enough energy out here. And yeah, it's all bigger than your threshold for worrying about internal charging. But note that these are 10-hour averages. The instantaneous current is small. 10 centimeters, this is the integral flux in electrons per centimeter squared per second, but that's a 10-hour average. It fluctuates a lot. And it really gets ugly when you're in the radiation belt, but you don't stay there very long, and we don't operate there. We just pass through as quickly as possible. And I like to show this slide because some of my colleagues aren't convinced that solar particle events are a charging environment. Look at the electron kinetic energies and look at the particle flux. Yes, it is. This can get you into a geo-like situation. This was measured by the Spacecraft for a October-November 2003 solar particle event. It's the famous Halloween storm that Canadian children found so interesting because of the auroras during trick-or-treating. Now, another useful tool from our ultra-conservative friends at JPL. This is a map of your surface charging risk as a function of your latitude and altitude. GPS vehicles operate where I put the white arrow right now, which is one reason they're arcing and sparking on the surface a lot and contaminating their PV arrays and losing power faster than anyone thought they would. The other interesting feature here is that all the way out at 100,000 kilometers, halfway to the moon, at 0 degrees latitude as viewed from Earth, you've still got a high-risk environment. Isn't that interesting? Otherwise, everything is kind of moderate, medium, or no issue, unless you're where space station goes every day during its high latitude passes. Oh, something else to mention about that. Garrett and Whittlesey's Guide to Mitigating Spacecraft Charging Effects, the book, is available free of charge at that link. JPL is giving it away. You don't need to buy one. This is an internal charging threat map, which looks a bit different. This one is described in terms of orbital inclination. Geosynchronous orbit is right there. And you can see that where the proton belt and electron belts are pretty easily in traffic. And once again, GPS satellites operate in here. One of the reasons that they're not all operating all the time. Let's do a simple work example that shows you how to use a current balance equation. I don't have an audio-visual edit here, except this one. Imagine this is a simple PV array. I've got a string of cells that has a length and a width. In sunlight, the cells have a voltage, V. We're going to make it 130 volts, 160 volts in an example like station. And it's connected on its negative end to structure ground. I want to be able to calculate floating potential as a function of position along this. Can I do that? Well, yes, because I've made a simple geometry that lets me cheat, basically. At steady state, the ion and electron currents will be equal. The expression for the ion current and the electron current can be put into a ratio, and you can start canceling things, and you end up with this. But let me point out the key difference that makes this work the way it does. Remember, Boltzmann's equation applies. We have a temperature, and the heavy things are going a lot slower than the light things. The velocity of the electrons, just the gas kinetic speed, is a lot higher than the orbital velocity of the spacecraft. So they're coming in from every which direction as fast as they can. The ions, in contrast, are being picked up at space station orbital velocity because they're not going fast enough to do that. Then you ask, well, why don't the electrons come into the backside too? Well, they try to, but they separate from the ions. That creates another field, slows down the electrons, speeds up the ions a little, and you still have a wake behind the wing when the active surface is facing down the velocity vector. Can't pick up any charge back here if your velocity vector is that way. So I just do the ratios, and that's just the Boltzmann expression for the collection of particles with some velocity VE on a flat surface. And then you do the ratio, and it turns out that only about 20% of that whole length is collecting electrons. The rest is collecting ions to balance the charge. When I do this, I can work out or calculate, it's just arithmetic. The voltage is a function of distance from one end to the other. And as it turns out, the negative end is at minus 130, and the positive end is about plus 30. Most of the wing isn't collecting electrons at all because it's too negative. And that's what a lot of folks, or some people, thought would happen to station early on. And this calculation does work for a number of satellites that meet this key criteria. Exposed metallic PV cell interconnects and collection buses. There's metal that can collect the electrons in RAM. This doesn't work on ISS at all. Why? Well, that's because we buried the interconnects between the cells and the current collection buses in dielectric. The only way ISS can collect electrons from the ionosphere is around the solar cell cover slip edges on the edge of the solar cell. So that's why we're seeing not very much charging from the PV array wings, a lot smaller than originally anticipated. And the two 10-amp plasma contactor units are way too much gun for this. And that's why we don't use them much or at all anymore. So the steady state assumption is also not valid given the size of the ISS as a capacitor, which is greater than 10 to the 9 picofarads. And we do have a detailed model, not one of these toy calculations, Boeing developed, and we're doing really good, accurate predictions of what happens if we know the ionospheric temperature and density. Now, something else is going on, however, in addition to PV arrays collecting electrons, albeit a lot fewer than we thought they would. We're flying through a magnetic field at 7.8 kilometers per second. And that looks like this. And the reason this graphic at the lower right shows station at high latitude. I don't know what latitude that picture really is, but we'll just pretend it's at 51.6 north. And the reason the B field vectors are going into the page is that The south geomagnetic pole is near the north geographic pole and vice versa. So your field lines operate the way you'd expect for that. Using the same simple arithmetic we used for the PV array and using 50 volts, which is the tip-to-tip voltage difference along that 100-meter truss at high latitude, we calculate that the negative end will be minus 42 and the positive end about plus 8, and we see something very close to that. Bear in mind that this motional EMF depends on orbital velocity, and the EMF is zero at geosynchronous because you're not moving relative to the field anymore. We learned a lot of this using our floating potential measurement unit, which is shown here in the lower right-hand image and is mounted there on station these days inside that red circle. First, very early after it was deployed, we got some overflights of Millstone Hill when the radar was operating and doing what they call world days to study ionospheric properties. The red and blue circles are the density of electrons and temperature of electrons. Millstone Hill was reporting, and the lines you see here are what the FPMU is reporting, those continuous. So we're really making very good measurements compared to a completely different method for doing that. We followed up later in life with orbital conjunctions with the Department of Defense CNOF satellite that had a Langmuir probe on it. You can see from the regression line that as long as we're above mid 10 to the 11 densities, the agreement is remarkably good there too. So we have confidence in our instrument by validating it against two independent measurements. Now, this graph speaks volumes, and we could spend a lot of time talking about it, but this is 4 orbits with the plasma contactors off. The starboard tip is doing that, and the port tip is doing that. You can see when the port increases negative voltage, starboard goes down, and vice versa. Also, they get a little bit positive when the starboard tip is very negative. The port tip is a little bit positive. You saw that from the drawing beforehand. Superimposed on these magnetic motional EMF voltages are these peculiar spikes, and that's the maximum solar array-driven charging we've ever seen. Collecting electrons around the edge of the cover slips can give you up to 45 volts on a day when you've got that kind of temperature and that kind of density. And when we turn the PCUs on, all of that kind of goes flat. We still have our magnetic induction happening, but it's shifted because the plasma contactors are on the truss axis in the middle and clamp that to 10 volts negative. So the structure is still picking up motional EMF voltages anyway, collecting electrons, so the two ends are going up and down. But the PV array-driven charging is completely suppressed. And then we saw something completely different. Operating the floating potential measurement unit when our electrical power system folks were doing efficiency measurements on those big 160-volt wings, whenever they did a full wing unshunt at eclipse exit, we saw really big voltage spikes that lasted a few tenths of a second. Well, why is that happening? That's still the subject of forward work, but I will simply mention that the charging and relaxation time is on the order of milliseconds to seconds, and the relaxation time is dependent on ionospheric density. So if I've got a 160 to 300 volt wing on my gateway platform, and I'm not running my ion engine, so I don't have an artificial ionosphere, and I do a shunt, we don't know what's going to happen, but it looks like it could be an issue. It could be a safety thing to be concerned about. We don't necessarily want to. That could be on the don't do it command list, possibly, if it turns into a problem. But we believe there are a couple of different approaches to explaining this, but the one I found most satisfactory came from one of my Boeing colleagues, and it's displacement current. Remember, the capacitance shielding thickness contributes to the capacitance of the entire structure, and when you do abrupt voltage changes, displacement current leads to big voltages that are transient like that. So, where else might we encounter ionospheric plasmas in magnetic fields like those we experience in space station? In the inner solar system, well, you probably aren't. Mercury is the only planet with a magnetic field, and it's only about 1% as strong as Earth's. The Moon, Mars, Venus, and near Earth and main belt asteroids have insignificant global magnetic fields. Where are we going to find cold, dense ionospheric plasmas like Earth? Well, Venus below 420 kilometers, Mars below about 200 kilometers. If I don't need an ionosphere, I'll just decide to fly higher than that, and those are kind of high satellite drag environments anyway. But there's one other place I've mentioned in passing that many people wouldn't expect, and that is completely surrounding your 200 kilowatt class high thrust interplanetary transport with electric propulsion. It's making its own ionosphere when the engines are running. If the EPS, the electrical power system, is photovoltaic, which unfortunately it will be until we get smart and really invest in space nuclear power, we can expect high string voltages for efficiency in very large PV array areas for total power requirements. So there are some risk questions to consider here. And we can learn something from what we've seen on station in managing these risks. How much PV array-driven spacecraft charging can I expect when the electric engines are operating? Well, I operate PCUs when I operate electric engines, so the electric engine doesn't charge the spacecraft. So I've got a PCU operating, and if these things are collecting electrons, it doesn't matter. The PCU will take care of it. So if I'm operating thruster neutralizers with the thruster, no problem. What happens to the vehicle floating potential when the high voltage strings are unshunted? We don't know, but it looks like it could be a problem. What happens if the electric engine neutralizers degrade or fail? Well, Hall effect engines operate at 300 volts, and if you had partial failure or degradation of your thruster beam neutralizers, you could easily get 100 volts on your vehicle for a while before you completely get up. And you want to prevent that. Now, using nuclear power reduces this risk, but it doesn't eliminate it, because thermoelectric power conversion units look a lot like photovoltaic array strings with interconnects. They can still collect current from the plasma. But given that this is only happening with electric propulsion, which is probably going to be, I say high thrust, compared to chemical, obviously not, but compared to traditional or conventional electric engine jets, you're going to have to increase the amount of available power, which determines thrust for electric engines, so you can get your delta V into a practical window for human spaceflight. You don't have 3 years to do this, you only have a few months. That means they will be operating lower impulse, higher power, makes the wing bigger, drives you to a reactor eventually. By the way, one of the reasons, as an aside, that the Gateway platform is being used as a departure point, I'm sure you've all heard that low Earth orbit is halfway to anywhere in the solar system. Well, as it turns out, halfway isn't far enough. In that distant retrograde lunar orbit, you're a lot more than halfway to Mars. So that electric propulsion system can get you there and back in a couple of years. What that means is you put the entire cost of the, instead of launching a whole bunch of propellant to LEO, you launch less out here, and you put the cost of all this back on your expensive launch system. It seems to be working for people who worry about money, like me. Now, before flight, no one in the program really believed the station would ever fly through an aurora. Then, on November 12th of 2000, Commander Shepard reported the following. Transited through a very unusual aurora field. Started out as a faint green cloud on the horizon. Grew stronger as we approached. Aurora filled our field of view from the service module, nadir ports, as we flew through it. A faint reddish plasma layer was above the green field and topped out higher than our orbital altitude. As it turns out, that hasn't been unusual at all. We do it all the time. And it looks like that. And if you've got green under you, some of the electrons that were headed that way to contribute to the green didn't make it. They ran into your spacecraft first. And we've seen that happen. Come on. from time to time. This is an example of auroral charging on a European spacecraft. Number of events versus voltage, most of it's small, but there are a few, 2-4 kilovolt events over this time period, and Freya was designed not to have charging problems. It was completely covered with indium tin oxide, grounded and bonded properly with static dissipative PC boards, just everything, so it did not have an issue. Now, I'm going to go through another simple worked example, and this one is how auroral electron streams charge spacecraft using a very simple capacitance model. V is equal to Q over C. V is the charge I need to make that voltage happen with that capacitance. So my charge is going to be what I can collect on the surface area of that spacecraft in 10 seconds if I've got a normalized current of 2 times 10 to the minus 5 amps per square centimeter. I'm going to decide the voltage is 30 kilovolts, which means that the capacitor can charge to 30, but not more. And I'm reporting this as net current. The net current of the spacecraft is the auroral current minus secondaries plus photoelectrons plus ions. And that's what happens when you do the arithmetic. A 1 meter sphere in free space has a capacitance of a few hundred picofarads and charges all the way to 30 kilovolts in less than a second. I put a 10 micron dielectric film on that same sphere. The capacitance goes way up, and now I only go to 2 kilovolts in the whole exposure time. Same kind of thing happens for the disk. Now, space station doesn't have a capacitance of 1 million picofarads. It has a capacitance of 10 billion picofarads. So that same auroral stream charges it to 13 volts, we expect. And the spacesuit only charges to 27, which is a good thing because several astronauts report having done actual EVAs in auroras. Well, how do you know you were in aurora? Well, it was green there, and it was red there, and it was the same way all around, so I think I was outside in an aurora. And we say, yeah, that's true. But there was no big threat, just because the capacitance of the EMU unit was high enough to null that out, really knock that down in a big way. And what evidence do we have that this is all true? Well, in 2008, on day 86, station flew through a high-latitude auroral event, and the floating potential measurement unit reported an increase of about 18 volts. And both Langmuir probes reported an increase in electron density at the same time because the auroral electron stream was ionizing the upper atmosphere more than usual. ISS was in the auroral zone for 144 seconds, but the actual arcs, the green things you see in the sky, were of much shorter duration and about 12 seconds. But we observed 18, and you remember in the previous simple toy calculation, we got 13, pretty good. And the Defense Meteorological Satellite Program confirms that when we were on that flight path, we were in a region at a time when densities were above 2 times 10 to the minus 5 amps per square centimeter along that flight path. Now, the reason we were charging the frame of station has to do with that very thin anodic chroming that makes a capacitance so big too. 30 kilovolt electron can go right through 30 microns of chromic acid coating and deposit in the structure. So, we understand all of this. And what does the DMSP itself do? Well, it charges various surfaces to much higher voltages depending on what the surface is made out of. The highest voltages are Teflon. The frame is much smaller, the structure is much lower. Kapton doesn't charge as much as Teflon, and they started getting static dissipative since this event happened because that vehicle got damaged. But note that individual dielectrics are conducting structure charge differently. And how does it work for a complex spacecraft like this? Well, it looks like an assembly of smaller capacitors, doesn't it? With a common ground on one side. Somebody said that we're not grounded in space. In fact, we are. The ionosphere is our ground, but it's a weird ground because it acts like a diode and it doesn't necessarily carry that much current unless you have a plasma contactor. In interplanetary space, that's even dicier, but still, your electrical environment you're surrounded with, the plasma you're flying through, is your local reference ground, even though you've got a station or a vehicle structure ground inside the spacecraft. That refers to your structure potential. So the floating potential, when I use that term, is really measuring the structure of the spacecraft relative, or whatever surface, relative to that environment. I'm still treating that environment, no matter how diffuse and how limited its ability to provide current, as the local reference ground. Now, I showed you the geomagnetic storm before. This is interesting because this drawing is to scale. The moon is way out here. Earth is way over here. And isn't it strange that we can get geomagnetic storms out here downstream, downwind from Earth that look like this, with electrons being fired at Earth from the reconnection site and then out toward the moon, where it does interesting things that we need to make sure won't hurt us. Now, why are we talking about the geosynchronous environment if we're going to go to the moon and Mars? And the Cislunar answer is kind of obvious. I'm going to be in it a few days every month, or when the geotail is whipping around and I end up in it anyway. Mars is less obvious. But the geo-environment is widely considered to be a worst-case hot plasma and energetic particle spacecraft charging environment for the inner solar system. Only Jupiter and Saturn are worse, but we're not going there anytime soon. So the natural environment's definition for design specification for Orion, SLS, Space Launch System, and Gateway all use SLS Spec 159 with the geosynchronous charging environment. This defines the environment, but it doesn't tell you what to do about it. But the Orion 70080 document, Cross-Program Electromagnetic Environmental Effects, does, and calls out specific design to requirements for static dissipative properties of surface coatings, printed circuit board, shielding thicknesses, and all of that. So, spacecraft functional verification to the SLS Spec 159 extreme geodesign environment by tested analysis is going to be a contract requirement for those spacecraft. Or actually, it already is. Now, there's something about surface charging in the geosynchronous environment. I think I've mentioned this already. The currents are lower than we see in the auroral environment, a lot lower. They're lower than the photoelectron emission, so if you're in sunlight and you're seeing this kind of current to your surface, you're going to charge positive anyway, 10 volts maybe, at most. However, spacecraft have complicated shapes, and some of them can be in shade while some of them are in sunlight. So we want static dissipative surfaces again, so that with this kind of a current, we can equalize that charge over the spacecraft before the shadowed region goes to minus 20 kilovolts and arcs to the unshadowed region. Static dissipative materials let you do that again. If that current gets a lot bigger, then maybe you need to do something different. Maybe you need to have an active detection of surface charging threat with plasma contactor operations on demand to create a static dissipative environment around the spacecraft. Both Department of Defense and commercial ComSat operators are using some of this now, but not a lot. The other problem we have is deep dielectric charging. And plasma contactors do no good for that because they're outside the spacecraft, and I'm not sure you'd want to run one inside your avionics box. That could be a problem. But in this case, dielectric time constant becomes a design driver because deep dielectric charging happens in time frames on the order of hours to days. Primary spacecraft internal charging targets are insulators like cable wrap, wire insulation, circuit boards, electrical connectors, feed-throughs, and arc tracking is one of your biggest threats here for power systems and power cables. Now, These are JPL and Aerospace Corporation recommendations. Looking at the permittivity of the material and the resistivity, we have some lines here corresponding to various charging times. Note that Kapton and Teflon, our favorite LEO materials, are in the don't use it zone, and for good reason. Anodized aluminum is over here too, but I will point out that Kapton and Teflon have been used successfully when they are doped with carbon black or nanotubes or something like that to make them static dissipative, if you can take the hit on your thermal control properties. Now, the moon has no atmosphere capable of blocking solar wind or energetic particles, so orbiting spacecraft and the lunar surface are exposed to similar charging environments. Lunar orbital surface charging threat environments include a few days on each side of full moon, plus whatever you pick up from the geotail and neutral current sheet moving around, and solar particle events, and I should add coronal mass ejection passage. Lunar Prospector observed did cislunar charging observations. During a solar particle event, the night side of the moon went to minus 4.5 kilovolts and spacecraft potentials to minus 100 to minus 300. Now, I showed you a table earlier where the Debye or shielding length was only a few meters, and Lunar Prospector was a lot further away than that. So your question ought to be, how did they make that measurement? They made that measurement with electron spectrometers that get kinetic energy of the incoming electrons. If it's 4.5 kilovolts relative to the spacecraft spectrometer ground plane, they saw it because their aperture was only looking at the lunar surface or some part of it. Similarly, they can look at electrons coming in from the local environment and the solar wind that are low energy and see how that changes their spacecraft frame potential. Lunar Prospector also made the first observations of geotail current sheet charging. Lunar surface potentials, even in sunlight where we have photoelectron cleanoff, could go up to 1,000 volts negative, while the spacecraft potential is between minus 40 and minus 80, which isn't so bad. More recently, the Artemis-Themis constellation has done these charging observations and essentially confirmed the kind of thing Lunar Prospector reported. So the geodesign environment should cover the expected conditions, because what we're seeing is that the cislunar environment is similar to geo, even during particle events, similar to auroral charging, but less severe, we think. However, that's 2 spacecraft over a period of 20 years. I'm kind of thinking we could use some more data here, but we can proceed with reasonable confidence and safety by simply designing and verifying to the geo worst-case design environment. Now, I've mentioned space weather messing with us before, and I'm going to go out again. This is kind of a hobbyist site, but it's useful in that you can go here and look directly at the solar wind. You can go here and look directly at the X-ray data from GOES. And you can buy dolls for your children if you like that have flown on stratospheric balloons by a high school in Bishop, California. They've been doing that for a while. And if I go down now, what do I want to do here? That, okay. The real resource, and that's where spaceweather.com gets all of its good stuff, is here. You can look at coronal mass ejections from SOHO until SOHO dies, which could happen any day because it's 30 years old almost. You can look at the auroral circle. You can look at our ghost proton flux and see if there's a particle event and do we have an X-ray flare, and is there a geomagnetic storm? But what I want to show you is not the models in the reports, but the actual observations at geo of the electron flux. 10 to the 3 particles per square centimeter per second right there, there's a dotted line, and that's your alert condition for internal charging. These are greater than 2 MeV electrons, total fluence, and these are 0.8, which can still do internal charging, albeit at lower depth, and contribute to surface charging. I've often wondered about why 10 to the 3 is the alarm limit, because it spends almost all of its time above the alarm limit. I've been watching this for about 20 years now. But I recommend, you can see from the directory at the Space Weather Prediction Center that this is a massive resource, and it's worth your time if you're interested in this at all to go work through it and have a closer look. Now, if an event happens that violates your design requirement, there isn't a lot you can do to save a vehicle for this kind of charging process. If you're worried about arc tracking on your PV arrays or your power system, you can shunt the wings and power down. Then the power supply can't drive the arc track, but then again, your batteries are going to die pretty fast, and that's loss of mission. That's why I keep emphasizing it has to be designed out. And it's designed out by becoming familiar with NASA and DoD standards and guidelines and preferred practices for managing spacecraft charging that capture the lessons learned from all of those spacecraft that died in the 70s and 80s. You can have a close look at the JPL Voyager spacecraft charging design and verification process, which is documented here. And while that looks like the kind of time and effort and schedule hit that would make most managers crazy, if they hadn't done this, Voyager would not have survived the Jupiter and Saturn flybys. This charging would have taken it out. Shielding and static dissipative coatings are important, and also important are grounding, bonding, and EMI-EMC compatibility. If you're someday you're gonna arc anyway, you want it to be harmless. Your spacecraft dock at 2 different potentials, you want it to be harmless. If your avionics system layout complies with these requirements, then nothing interesting will happen. You can also ask about active control during severe charging events if you expect that kind of thing to happen periodically. And then you're going to want a PCU or something like it, a plasma contactor unit, but they eat a lot of gas, so you don't want to run it continuously. You need a detector on board like the AmpTech C detector that was built for DoD. It's a simple, small instrument. Remarkable that it costs $1 million per unit given its size, but it does. No, they were at risk. They were at risk for other charging events inside. It was deep dielectric charging and surface charging. No, they were radioisotope units, so they didn't have solar arrays. But if you don't have solar arrays, it doesn't mean you don't have high voltage cables that could get you. It didn't have high voltage cables either. Their concern was really, am I going to arc on my PC boards? Because at the time, static dissipative PC boards didn't exist yet. They had not yet been developed as a result of this. Yeah. Say again? Yeah, Juno is designed to survive the charging environment. Juno also has a 1 centimeter titanium safe for its avionics, primarily because the total ionizing dose in the Juno orbit will even kill rad-hard parts in less than a year and a half. So that much shielding is to block the energetic electrons, which at the same time removes the deep dielectric charging threat to the boards inside. Yeah, I think we need nuclear. But that's just me. Nuclear electric Vasimir would make everything so much simpler, and that with Falcon Heavies to launch at reasonable cost. But you know, I'm retiring soon, so I don't worry about it. Now, this is the story I was telling you earlier about ADIOS 2, a big $500 million, $2 billion Japanese Earth observation package. Polar Sun synchronous orbit, 800 kilometers, same as DSP, kind of DMSP, and with an orbital period of 101 minutes. On 23 October 2003, during a geomagnetic storm, well, actually during an auroral event. I think that was a high velocity solar wind stream that caused that, so I shouldn't say it's a big geomagnetic storm. Something happened at 2349 on UTC on October 23rd, 2003. The satellite switched to light load operation because of an unknown error. This is intended to power down all observation equipment to conserve energy. By 2355, the satellite was dead. Further attempts to recover telemetry failed. JAXA determined that the total loss of ADIOS-2, a polar Earth orbiting satellite with a bus voltage of 50 volts on the PV array, was attributed to interaction between the auroral electron plasma environment and the improperly grounded MLI around the main EPS wire harness. Didn't hurt the wings. They built one of those arc tracking bombs with the twisted pairs at opposite polarity and the wrong installation on them. The loss of ADIOS-2 investigation revealed that auroral charging of a polar satellite could cause serious failure, including total loss, and I'll say, yeah, if you build it wrong. And MMOD impact could have done that too, but there's more to this story in that those 50-volt wires that were carrying many amps were insulated with Tefcel, which was real popular at the time because everybody was upset about Kapton arc tracking. Well, this Tefcel in this configuration was running 20, 30 degrees centigrade over its maximum recommended use temperature. Its additive package was outgassing away, and it was becoming brittle. It cracked. Now, that's what enabled the little arc on the ungrounded blanket, metallized plastic MLI blanket, to start the arc track that killed the vehicle. But without putting too fine a point on it, that configuration would have gone all by itself eventually. So look what you had to do to make this happen. We didn't ground the metallized part of the MLI to structure. We used the raw material, and we configured it so that it would be an arc tracking bomb. And that should never have gotten past PDR. Not much less CDR, but it happened. And that's the end of my talk. Unfortunately, I've, without thinking about it, ended with a catastrophe story instead of something fun. So, are there any questions? You have to get NASA to start funding nuclear power in space. It was a very small project. They're doing a 10 kilowatt reactor development right now. So it's baby steps. You have a lot of public concern about this. I'll say it can be perfectly safe. And the people all say, yeah, we heard that before. And it was funny when I was at the first International Gateway meeting, the Russians looked at this gigantic solar photovoltaic array that would have to run at a kilovolt for efficiency because the conductor runs are so long and the ohmic losses would be so high. And they just said, this is stupid. Look, guys, we've got a 1 megawatt space nuclear reactor in late development. We'll give you a real good price on it. And nobody bid at the time. But this was like 4 years ago when Russians were less unfriendly than they are now. So you have to start building it. Franklin Chang Diaz's Vasimir engine needs 1 to 10 kilowatts of something. And let me mention why the Prometheus project was canceled. Vice President Dick Cheney decided it would be a real smart cost-saving move to adapt submarine nuclear reactors to the Prometheus vehicle. Submarine nuclear reactors operate in the ocean, so you've got plenty of cooling water. But when you're in space vacuum, the only way you can dump waste heat is with a radiator. And the radiator got so big it was the end of Prometheus. But that was 30 megawatts. It doesn't have to be that big. Also, you have a general problem with going to Mars if you're anytime soon, if your federal budget is clamped at $20 billion, less than, per year, and has been for 4 administrations. So I keep telling some of my colleagues who go on about new technology to do this or that. No, you don't need new technology. You need money. You need a budget. And until that happens, and that's one of the reasons Gateway has become attractive. Building a small man-tended space station that orbits the moon. The first time that was presented to the higher powers, they said, no, I don't want to build that. Then they looked at the price tag on everything else and said, yeah, the little space station around the moon with an international partnership. Yeah, we can buy that. I want to buy that international partnership. And then you can talk about getting ready for Mars out there or whatever. But that's what I'm willing to pay for, because the cost of everything else, I'm not paying for that. Political science.
It seems like you could pretty much charge the spacecraft, but just
that's how electrodynamic tethers work.
yeah.
If you don't have a magnetic field, that doesn't work anymore.
But you could do it, would that work all the way out from the ionospheric?
Well, your velocity is zero out there, so your tethers don't work anymore. And around Mars and the Moon, no magnetic field.
Yeah. But in low Earth orbit?
In low Earth orbit, electrodynamic tethers could work, and actually HTV flew a demonstrator, and it surprised me that the station's safety review panel allowed it, because it deployed its counterweight upward after HTV had separated from station, and that's the kind of configuration where the cable breaks, and then you've got a collision hazard with station. So the Japanese had to show that given our cable length and our orbital mechanics, if it breaks, it can't get back to station altitude. And then everybody was happy with it.
I guess it speaks back to 1980, there was another, I think it was a CSAT, that lasted for several months on orbit and had a breakdown. So you guys,
Yet, I don't know the CSAT failure story. One of the earliest big spacecraft charging events was a defense communication satellite in the 70s and its antenna. Its communication system failed. Nobody knows why to this day. It's still there. You can look up its ephemeris and look at it through binoculars as it flies over, if you wish. But that was one of the events that got DoD real interested in spacecraft charging threats.
yeah, I guess correspondingly, if you had current thinking generally from the atmosphere, you also could get, by having a current board, you can have an electromagnetic force you can use for navigation. Well, I'm using a tether for
oh yeah, you can use tethers for propulsion. You can use tethers for orbit maintenance. You can use tethers to generate electricity, but energy is always conserved. So if you're generating electricity and using it, you're losing altitude. You're going to have to do something eventually to reboost. If you're generating thrust, then you're using power. You're eventually going to have to recharge your batteries or find a power source to drive all that.
I guess another exposure to this sort of thing is only rich is the magnetosphere actually keep reopening the solar panels too. Charged particles that you have not marked into the solar panels.
Displacement damage. It also gets optocouplers and optoelectronics inside the spacecraft. That's driven mostly by protons and secondary neutrons. So displacement damage. I'd mentioned DMSP poisoning itself with arcing contamination on the PV arrays, and that's because the expected decay rate of those arrays cannot be explained with displacement damage alone. Something else has to be happening. And the smoking gun evidence came from looking at the GPS. And there are some antennas on these vehicles that were reporting signals that had to come from the spacecraft, not from down there. And that turned out to be arcing signals, and the arcing is often enough to explain contamination deposition on their arrays.
Thank our speaker. And you have to pick up the paper and stuff here in the front. And also, reminder, next week is going to be our final talk of this And it's going to be Craig Watson, I want to say, from Lamont Aerospace, also talking about the International Space Station. And I'm also, after next week's lecture, I'm going to give you guys final instructions on what's going to go on for the student presentations, which are going to be the following week. So think of that as your final exam.
Now you have that on this machine.